Oh, it's all good? Okay, cool. And I had a clicker down there.
All right, so continuing on with the session, so we'll have Peter Nelson talking to us about infinite matroids on lattices.
All right, thank you, Spencer. And thank you for the organizers for making this happen. It's really, really nice to see familiar and new faces in the same place for the first time in a while. This is intended to be a jet lag friendly talk. My goal is really to just show you a pretty definition at the end of the talk. If you're at Waterloo or LSU, then you will have seen a talk on this topic as well, or you may have seen. The punchline is slightly nicer. We've got to a better place, so the ending is different, even if some of the story is the same. This is joint work with Andrew Fulcher. He's in the audience. He visited me from Ireland for a few months earlier this year and answered lots of stupid questions about lattices. So I wouldn't normally start a talk at this conference with the definition of a matroid, but it's on this slide because I'm going to be fiddling with it. I'm going to be talking about generalizing this definition to a larger context, so I thought I'd show you the definition in one of its usual forms. This is the definition of a matroid in terms of the independent sets. So we've got a non-empty collection of independent sets that's closed under taking subsets. That's what the second axiom says. And the third says that if I have a smaller and a larger independent set, I can add something to the larger and remain independent. I can add something from the larger to the smaller and remain independent. Some of you will know and some of you won't know about generalizing this definition to infinite matroids. If you look up the definition of a matroid in Oxley, then he'll tell you that matroids are finite by definition, and I've included that here. But it's quite possible to define infinite matroids. You just have to be slightly careful. You can't just say, forget this, and allow the matroid and keep the same definition and allow the ground set to be finite. You run into problems with cardinality. And in fact, there's lots of missteps you can make when you're trying to define a sensible notion of infinite matroid. There were various competing notions through the 20th century, and they all had shortcomings, or many of them had shortcomings, such as you don't really have duality. You allow things that you really don't want to be matroids, or you don't allow things that you do want to be matroids. So you actually have to take some real care in defining an infinite matroid in a sensible way. But you can do it. So what happened is that in a paper where he considered a few different notions of matroids in the late 60s, Higgs wrote down a definition of something called a B-matroid. And it turns out that B-matroids are really the right notion of infinite matroids. It's easy for that fact to be a little lost if you're trying to read Higgs's paper, but there was a paper much more recently by Brun, Distel, Kriesel, Pendarving, and Wallen that really gives a completely compelling argument that this is the right notion of an infinite matroid. So what you have to do is, instead of talking about cardinality in this third axiom, you can phrase this augmentation axiom in terms of maximal and non-maximal independent sets. So there's no set cardinalities here, so this is a much better way to think about infinite sets. And then you need this other funny axiom called IM, and it says that if I have an independent set I contained in a set X, then I will be contained in a basis for X. That's all it's saying. That's something that's just trivially true for finite matroids, because finite objects you can find maxima, but you really need to insist on this to stop silly examples that you don't want to be matroids. Now, why is this definition nice? It's because you can do all the things that you want to do with matroids. You can take minors, you can take duals, they interact with minors in the expected way, and there's a lot of different equivalent ways. I mean, there's cryptomorphism. You have basis axioms and closure axioms and circuit axioms and such. So there's really quite a nice picture, and I've thought about infinite matroids quite a lot in the last few years, and I used to be deeply suspicious of them, but I quite like them now. They really, nearly all of your intuition for finite matroids will carry over as you'd expect to infinite matroids. Sometimes the proofs are different because you can't do induction on the sizes of sets, which is a common tool. But there are ways around that, and really infinite matroids I think are quite lovely. So that generalization, sorry, the X is just any set. Oh, what's happening here? Oh. So this says that if I is a subset of any set X, then I should be contained in a basis for X. Is that clear? Okay, so infinite matroids in terms of the definition have just been sorted out. It is a solved problem. I'm going to talk about generalizing this definition further in quite a different direction. So on my next slide, I'm going to take quite a different tack. On the left here, you see a picture of a very small matroid on 4 elements. It's a triangle with a parallel extension. And on the right here, you see the Boolean lattice. So this is a picture representing all the subsets of the ground set of this matroid. So you've got the empty set at the bottom, A, B, C, D at the top. And the edges in this picture represent adding or removing an element to a set. So AC here is adjacent to ABC and ACD above it, and adjacent to A and C below it. And I've colored some of the points in this picture red, and they correspond to the independent sets of this matroid. So for instance, AB is a dependent 2-element set, so that is a non-red point, whereas all the other 2-element sets in this matroid are maximal independent sets, and so they get red points. Now it seems I'm wasting a lot of ink by drawing this picture to where I could represent the matroid much more simply with this picture on the left, but some of the properties of being a matroid are actually completely visible when you look at the picture on the right. For instance, anything below a red point is going to be red because all the subsets of an independent set are independent, and all the highest up red points are on the same layer because all bases in, for example, this matroid and all other matroids have the same size. So this picture does tell you something even if it's not particularly useful looking at this point. You can learn more from this picture if you apply some more colors. So what I've done is I've taken the same picture here and I've colored it by coloring the edges as well as the points in this picture. And the way I've done that is as follows. If I have an edge in this picture, then as I said, it corresponds to an addition of a single element to a set. If I add a single element to a set in a matroid, either the rank goes up by 1 or it stays the same. And so I color the edge red or blue according to which of those two things happens. So I claim that you can understand more about the matroid if you've colored this picture in this way. And in particular, you can think about red and blue paths, up and down paths in this picture in quite a nice way. So a red path from the empty set up to some element, that's a proof that that set is independent. So if the empty set goes up to BC, that means I can get from the empty set to BC, adding elements, and the rank goes up at every stage. So I'm looking at an independent set, and that characterizes the independent sets. And likewise, if I can get from some point up to the top via a blue path, then it means the set is spanning, because I didn't increase the rank at any point, and I went all the way up to the top. And then, of course, if a set is both independent and spanning, it will be a basis of a matroid. That's another way to define a basis. And in general, if I have a blue line from some x up to some y above it, then it means that x spans y. Having a red line from x to y means I can kind of add co-loops one by one to get from the set x to the set y. Now, when you look at this picture, you can ask about the structure of the coloring, and you can quickly see that there's certain things you will never see in such a coloring, and they are all examples of these things that lattice theorists call diamonds. So a diamond is just a pair of points in the lattice with a common neighbor below them and a common neighbor above them. Combinatorially, that's a set X, then X union E, X union F, X union EF. So for elementary reasons, you're just not going to see certain diamonds in this picture. Say, look at this one here on the top left. This is a diamond with two blue edges up the left and a red and a blue edge up the right. that would correspond to a set X where I can add E and add F and the rank doesn't change, but if I add F, the rank goes up. That just doesn't happen in a matroid because rank is a well-defined invariant, so you're never going to see a diamond like that in this picture. And for similar reasons, you won't see these four. You also won't see this one for a kind of even more dramatic reason. The most interesting one that you never see is the one on the bottom right. And this you don't see for a kind of submodularity reason. I'm never going to have a set X so that if I add E, the rank doesn't go up. If I add F, the rank doesn't go up. But if I add them both, it goes up. That just doesn't happen because of submodularity. So in fact, you don't see this. And in fact, this is a cryptomorphism. If you have any coloring of the edges of a Boolean lattice where you avoid these 6 diamonds, then your coloring came from a matroid in the way I described, and you could recover the matroid from that. So there's quite a nice little picture here. Now, this is a different picture of a lattice. This time, it's not a set lattice, it's a subspace lattice. So the 16 points in this picture are the subspaces of the 3-dimensional vector space over the 2-element field. There's one trivial subspace at the bottom, there's the subspace of everything at the top, and then there's 7 one-dimensional and 7 two-dimensional subspaces in between, and they're organized in this lattice structure via kind of adding, spanning, and containment, and so on. And I've drawn some red dots on this picture, and I claim that, well, I'm asserting that this set of red dots is actually the collection of independent subspaces in something that's called a Q-matroid. Now, before I define a Q-matroid, I'll show you an embellished version of the same picture along the lines that we did earlier. This is what you get by adding red and blue edges in a similar way to what we did before to this picture, and you get this kind of red-blue coloring of this lattice, which is no longer a set lattice, it's something else, but this coloring is very similar. So if I haven't made a mistake, which I have made 2 separate mistakes in previous versions of this talk with this slide, but I claim that if you check carefully and look at all the diamonds, you're never going to see one of those 6 forbidden diamonds in this picture. So this is an example of a Q-matroid. For me, the example is more illuminating than the definition, but of course I probably should show you the definition of a Q-matroid, which is here. Q-matroids were defined a long time ago by Henry Crapo, in fact, in his PhD thesis in 1964. And then they were rediscovered independently in the context of coding theory by Urius and Pelikan much more recently. Now, even though there's a half-century gap between these 2 citations, there's quite a nice story. Some of you will know Henry Crapo. He passed away just a few years ago. And in fact, he collaborated with these 2 authors in the later years of his life. So they got talking, and Henry was very happy that people were suddenly paying attention to this very old definition. And there's a quite nice literature on Q-matroids now. How's a Q-matroid defined? Well, it's with some familiar-looking axioms, at least 3 familiar-looking axioms. The first axiom, well, okay, what do I have? I have the lattice of all the subspaces of FQ to the n. So this is a finite-dimensional vector space over a finite field. The first axiom set, and then I've got a subset of the elements of that lattice, so a subset of the subspaces, which are called the independent subspaces. And then that subset has to be constrained by 3 rules. The collection of independent subspaces should be non-empty. It should be closed under moving downwards, so a subspace of an independent subspace should still be an independent subspace. And then you've got an augmentation axiom, which is very similar to the one that we know for finite matroids, except you have dimension instead of size. And instead of taking I union a singleton, you have to say I, the vector space sum with the one-dimensional subspace spanned by E. But morally, it's the same kind of thing. So you've got an augmentation axiom. So you have 3 very familiar-looking axioms. This last axiom you need for kind of technical lattice reasons. I'm not going to go through the statement of that, but I will show you a variant of this later on. So these 4 axioms together give you the definition of a Q-matroid, and Q-matroids are nice. They do what we want. They have well-defined minors. They have cryptomorphism. In fact, there's about a dozen different ways to define a Q-matroid. And they have duality. I've put a disclaimer. Duality isn't quite as pretty as it is for matroids because complement is not so well defined in a subspace lattice. You do have a notion of complement, but it depends on the choice of basis. So things fit together okay for duality, and it does many of the things you want, but it's not quite as perfect as it is for the matroids we know about. Okay, so this is a definition of a Q-matroid, and really the goal of this talk is I want to show you what I claim is a good definition of an object that generalizes Q-matroids and infinite matroids at the same time. Okay, to do that, we need to talk about lattices in the abstract. I've shown you two examples of a lattice, set lattices and subspace lattices, and these are examples of a more abstractly defined lattice. So a lattice is just a partially ordered set, L with a partial order, and it needs to have a meet and a join operation, which means that for every A and B, I should be able to find a maximal element that's below both A and B, which is written with this upwards wedge symbol called A meet B. Just think of intersection. And then A join B is like the union. That's the minimal element that's above both A and B. So not all partially ordered sets have this kind of structure, but the ones that do are called lattices. Now, the lattices I'm going to talk about are what's called modular. Now, for what it's worth, that's the definition of modular. I found when learning about these things that it took quite a while for modularity to really crystallize as a useful notion in my mind. So that definition, at least for me, the first time I saw it, wasn't very useful. For me, the useful way to think about modular lattices is that they are the lattices where the notion of height is well defined in the first place. I'm speaking roughly here, there's nuances, but modular lattices are the lattices that have a nice notion of height. For instance, size or dimension in the lattices we've seen. Right, so you've got these modular lattices, and really you can just think of modular lattices as nice lattices for our purposes. Now, modular lattices, they include these two examples we've seen, set lattices and subspace lattices. But there's some really exotic examples of modular lattices, and I wanted to give you just one that gives a flavor of they're not kind of as easy as you think from those two examples. I can take the lattice of all subsets of, say, the unit interval, it doesn't particularly matter, modulo finite symmetric difference. So I identify two subsets if they differ on only finitely many elements. Now that's a modular lattice with intersection and union as meet and join. But the weird thing about it is that it's got no what are called atoms. An atom in a lattice is something that is one step above the bottom, but there's nothing between it and the bottom. So set lattices, if I have a singleton set, there's nothing strictly between the singleton and the empty set. Subspace lattices also have atoms. This lattice doesn't have any atoms. You've got the thing at the bottom, but because there's no such thing as a minimal infinite set, there are no atoms. So lattices, even modular lattices, can be quite exotic, and a lot of the tricks you want to play, you just can't play for general infinite modular lattices. Now, the idea of unifying Q-matroids and matroids is not new. A number of people, including Dominic Welsh, who was mentioned earlier today, have thought about this problem. The generalizing objects have been variously called L-matroids and super-matroids. I think I prefer the latter term. It's the one I've used. So these notions, they did interesting things in their own ways. They all did rely on the lattice having a notion of height, and essentially the lattice only being finitely high. So they all did things like I move up one step in the lattice, and you can't do that for general modular lattices. So the definition I'm going to show you, it circumvents this problem of moving up one step in a lattice. It shows that you don't actually need that to get a sensible matroid-like notion. So here is the first definition of this object. This we call a supermatroid. This is not my favorite definition. I'm going to get to my favorite definition, but I'm showing you this one first because this is the one that looks like the definitions we've already seen. So we've got a modular lattice, L. It's got an element called 1 at the top and 0 at the bottom. You can kind of avoid that, but it's a bit nicer if you don't. A supermatroid is a subset of the lattice that satisfies 5 particular axioms. Now, in fact, all these axioms you have essentially seen, so I'll talk through them. The first one should be pretty clear. The collection of independent elements of the lattice is not empty. That's just like what we've seen for matroids and Q-matroids. The second is that it's down-closed. So if I have an independent element J, I've got some I that's below J in the lattice, then I should also be independent. You'll note here that I've demoted my things in the lattice to lowercase. For subspaces and sets, it makes sense to use capital letters, but these are just these little dots in the lattice. They're not sets that contain anything, so it's kind of nice to use lowercase. The third axiom is a kind of augmentation axiom, and it's very similar to the augmentation axiom for infinite matroids. You've got a maximal independent set and a non-maximal independent set, and you can add something to the non-maximal one and remain independent, except you can't talk about adding a single thing, but you can make something very similar work. And in fact, this directly specializes to the infinite matroid augmentation axiom in the context of set lattices. IM is this other axiom that you just need for infinite matroids, even on sets, and it just says that any independent element below some element X will be contained, or below a maximal independent element below X. And then IL, this is a simplified form of the Q-matroid axiom I said I didn't want to talk through in detail earlier. It's a bit easier to parse if you're familiar with matroids in the usual sense. It just says that if I have a set I and it's a basis for both X and for Y, then it should be a basis for their join. Now that's completely trivial if you're thinking about set lattices, if you just look at the definition of basis, but you actually need it even for finite Q-matroids to ensure that you don't get silly examples in the context of general lattices. So here is a definition of a supermatroid. Now, I mean, if I show you a definition, I have to convince you it's a good definition. I mean, anyone can write down a definition. I claim this is a good definition, but I'm going to argue that by showing you a very different definition. So the idea behind this other definition involves departing quite dramatically from how we usually axiomatize matroid-like objects. Instead of talking about a predicate on a set, like independence or being a basis or anything like that, we're going to have as our atomic notions what are essentially these up, down, blue, and red paths that I showed you earlier. So here we don't have any predefined notion of independence. I'm just going to define a matroid in terms of a relation which is x less than or equal to 0, y, blue, and for that I'm going to say x spans y, and then a red relation, which I'm going to describe as x cospans y. That's a slight deviation from the usual way that the word cospan is used for matroids, but it's convenient here. So I'm going to have a lattice and a pair of binary relations on the lattice, and the binary relations are only going to apply to pairs where I've got an x and it's below some y in the lattice. I'm going to say x spans y for the blue relation and x cospans y for the red relation. Now, I did mean to divide this slide up into pieces, so please just look at this first one. This first rule that I'm going to impose is just kind of a sanity axiom. It says that if x spans y or x cospans y, then x better be below y. These predicate, or this relation only applies to comparable pairs in the lattice. The second relation, and it sounds reasonable if I just say it, if x spans m and m spans y, then x should span y. That's a kind of a transitivity condition. This condition is also saying kind of a converse. So it's saying that if x spans y, then x should span every m between x and y, and also every m between x and y should span y. I would say that if you have any sort of a matroidal intuition for the notion of span, then hopefully this axiom sounds reasonable. But this is something we have to impose because of the generality of the setting. Sorry, I don't know why this is happening. Need to go back. And then we impose the kind of dual version of this, the exact same condition, but for this red comparability relation. So these are, I mean, whenever you have an axiomatization of matroids, you always have the interesting axioms and the boring axioms, and these are the boring ones. These just say that these relations only apply to comparable pairs, and they behave vaguely like something that's called span or cospan should behave. And then here are the interesting axioms. This clicker is really not liking me. The interesting axioms are these two. So at the top, I've got the three boring axioms that are grouped together at the top. The first interesting axiom, for me, this is the one that really makes it a matroid. It says that if x is below y, then I should be able to find some b that is co-spanned by x and spans y. If x is the bottom element of the lattice, this is just saying that every y has a basis. If y is the top element, it's saying something about a basis in a contraction of the matroid, in a sense, and it's saying something slightly more general for an arbitrary pair x and y. But it just says if I have an x and a y, I can draw a red line up to some b, and then a blue line from b up to y. And then the second axiom, the second interesting axiom says, essentially, I don't have the interesting type of forbidden diamond that I showed you earlier. Now, you can't talk about diamonds because we can't step up one and down one in our lattices in general, but we can say something like that in terms of meet and join. So this says that if I have a diamond like this, so x, y, x intersect y, x union y, and I've got red and blue like this, then that didn't actually happen. The only reason that happened is because x was the same as y. So this is a kind of no bad diamonds type axiom. You don't need this for set lattices, but you definitely need it even for finite Q matroids. And that's it. This is the definition that I really like for, it says super matro. I guess it should say super matroid. So a super matroid is a triple consisting of a modular lattice and a pair of binary relations obeying all these rules I've said. So there's these simple kind of sanity check rules at the beginning, and then this basis existence axiom here, and then a no bad diamond axiom here. And this is actually a really convenient way to think about matroids. If you know the span and the cospan relation, then you can recover all your favorite matroid notions using very natural language. An independent set is just something that's co-spanned by the thing at the bottom. A spanning set is something that spans the thing at the top. A basis for the matroid is something that's co-spanned by the bottom and spans the top. A flat of the matroid is something that doesn't co-span anything properly above it. A basis for a set is something that looks like this with the zero element and the set. And then the closure of a set is the meet of all the elements spanned by that set. You need a complete lattice for that, but you've got a reasonable notion of closure. But my really favorite thing about this is that duality and minors are nice. In fact, they're even nicer than they are for finite matroids. If you define a finite matroid, I mean, it's not immediate that duality and minors are well defined. You need to prove that they give you matroids. But minors are actually completely trivial here. If I take a lattice, so if I take an object satisfying these axioms, and I restrict to just some interval contained in the lattice, then it's clear that these axioms are still all satisfied. There's really nothing to prove. And also, if I flip the lattice upside down and I switch red and blue, then also I get exactly the same set of axioms. And it follows from those observations that minors and duality just exist immediately. There's no subtleties or complexities in proving that minors and duals are well defined. They're just taking a photo of the lattice and flipping the lattice upside down and switching colors. So in this sense, I think this definition is actually easier to work with in many ways than our usual favorite definition of finite matroids. Now we have cryptomorphism as well. The first definition I showed you is the one in the top left, and then the definition I prefer is in the top right, and we can go via some intermediate axiom set to show that they are equivalent to each other. And we have other versions of the axioms, and we haven't quite figured it all out. But it's looking good for cryptomorphism to work well. Things like circuit hyperplane relaxation are easier to prove than they are for matroids. And finally, I've got 1 minute to talk about this slide. You can do something with the rank axioms, and it's a little bit subtle because the rank axioms don't even work for infinite matroids. But there's a type of lattice introduced by John von Neumann called a continuous geometry, which is a complete adjective, adjective, adjective lattice. It's a special type of modular lattice, and it's the kind of lattice that has a notion of height. And this would correspond to something like the cardinality of a set, but also would correspond to measure if you're talking about a lattice of measurable subsets. And we can show that if you have an object that satisfies a very natural version of the usual matroid rank axioms, then it corresponds to one of our objects, one of our supermatroids. So hopefully you enjoyed that picture. I'll stop there.
All right, thanks for the talk. Any quick questions before I switch over to the next speaker?
I'm confused. Are you saying that this definition is equivalent to the infinite matrix?
It specializes to infinite matroids for set lattices, but it contains the definition of an infinite matroid and also a Q matroid. Yep. Yeah. The other 5 correspond to the rank going up by a different amount on the left and on the right. I can show you offline. I mean, it comes from fiddling around inside a lattice, but you can do it.